In the early 1900s, classical mechanics was highly celebrated. But all that changed when scientists began to question why do metals glow when we heat them up. They soon discovered that not just metal, everything around us radiates energy. Whether it's Newton's apple, the sun, or even our own bodies, all objects emit radiation. To understand this better, Kirchhoff came up with the idea of a blackbody, a special object that absorbs and emits all radiation. But it is not just an ordinary black colored ball. Picture it as a metal box with a tiny hole. When light goes into the hole, it bounces around inside and gets absorbed every time, never making it out. Want to learn how we came up with the idea of a blackbody? Check out our earlier video for the full story. Around 1890, Lamarck did some experiment that turned classical mechanics upside down. He found that while blackbodies give off different kinds of radiation, the intensity changes in a surprising way. For example, here at a certain temperature, blackbody radiates less infrared light. It emits yellow light the most and drops again for the higher frequency light. Then what was the issue? Well, classical mechanics thought that the intensity would just keep getting stronger and stronger, shoot up to the infinity in ultraviolet region. This mismatch was known as ultraviolet catastrophe. In this video, we will answer 3 big questions about ultraviolet catastrophe. First one is, why do blackbody radiate all type of electromagnetic waves? Second one is, why does the energy go to infinity? And the last one is, why is in the graph a straight line instead of a curve? To answer this question, physicists used 2 of the most popular classical theories at that time, wave theory and equipartition theorem. Let's start with the wave theory. This is a 2D representation of the blackbody cavity. When we heat the cavity, atoms in its wall start to vibrate, acting like tiny oscillators. These vibrating atoms generate electromagnetic waves inside the cavity. As the waves travel and bounce off the walls, they interact with each other and create standing waves, just like guitar strings. These standing waves have different modes depending on their number of nodes. The first mode is called first harmonica or fundamental mode. It has one antinode or maxima at the center, representing the lowest frequency at which the system can oscillate. Similarly, the second harmonica has 2 antinodes, producing a higher frequency wave. For the third harmonica, we have another type of frequency. It does not stop at third harmonica, but can go up to an infinite number of times according to the wave theory. So when these waves come out from the hole, we get all types of radiation. Now we know why we get all types of electromagnetic waves when we hit the blackbody, which can be observed from both experimental and classical graphs. But the main question is, how much energy does each wave have? This is crucial because it will allow us to understand why we got this curve. At the time, the most widely accepted energy distribution theory was the equipartition theorem. Rather going through all these theories and equations, let's understanding with a simple analogy. Imagine you frequently shop on 2 websites, Amazon and Flipkart. If you make a few random purchases from each site, the average amount spent will vary greatly. Now if you shop for hundreds of items, the average amount spent on each would start to even out. If we shop millions of times, the average spending will be the almost same, regardless of the individual fluctuation in spending. This is a typical statistical analysis. Similarly, equipartition theorem, which is also a statistical theorem, states that energy is distributed equally among all degrees of freedom, meaning average energy is same for all degrees of freedom. In our analogy, Amazon and Flipkart are 2 degrees of freedom, and the average money is same for both according to the theorem. Then what are the degrees of freedom for these vibrating atoms? For one single atom, the degree of freedom is 3 because it has 3 types of translational motion along x-axis, y-axis and z-axis. For a diatomic molecule, along with translation motion, it can have 2 independent rotational motion. So the degree of freedom is 5. According to equipartition theorem, the energy of the system will be equally divided among these 5 degrees of freedom. As we discussed earlier, this tiny oscillator creates all types of standing waves in the blackbody during heating. So what are the degrees of freedom of these waves? Each mode with a unique frequency is a degree of freedom. As we discussed earlier, a blackbody can create an infinite number of standing waves with varied frequency. As a result, we have infinite number of degrees of freedom. Average energy of these degrees of freedom will be same for all according to the equipartition theorem. That's why the total amount of energy radiated will be infinite. This illustrates how, despite each mode having a finite energy, total energy is infinite for blackbody radiation. So if we are obtaining infinite energy, why isn't the graph simply a straight line, indicating infinite energy across all wavelengths? Instead, we observe low intensity for lower frequency waves, while the intensity becomes infinite for higher frequency waves. The final piece of this puzzle is that normal standing waves are one-dimensional, which means each mode has 1 degree of freedom. As a result, the energy is equally distributed among all modes. However, standing electromagnetic waves are 3-dimensional, leading to different degrees of freedom for different modes. Let's understand this with another analogy. In one dimension, there is only one variable, x, and this is the number of modes of standing waves. So x cannot be equal to 0. In 1D, every equation has only one solution. The number of solutions represent the number of degrees of freedom. So every mode has only 1 degree of freedom. In 2 dimensions, there are 2 variables, x and y, and they cannot be 0. So the first mode is x plus y equal to 2, and this has only one solution, meaning 1 degrees of freedom. But for second mode, x plus y equal to 3 has 2 solutions. So in 2 dimensions, second harmonica has 2 degrees of freedom. Similarly, third mode has 3 solutions, representing 3 degrees of freedom. So as the number of mode increases, the number of degrees of freedom also increases. So higher frequency wave carry more energy. Now imagine in 3 dimension, where the variation increases even further. In 3D, the first mode is x plus y plus z equal to 3, which has one solution. But second mode has 3 solutions, and third mode has 6 solutions. So in 3D, the number of degrees of freedom increases more rapidly. In conclusion, higher frequency electromagnetic waves have much higher degrees of freedom, and consequently, higher frequency waves carry more energy. So according to classical wave theory and equipartition theorem, infrared rays will have the lowest energy, and from UV rays, energy will increase boundlessly, resulting what we have ultraviolet catastrophe. I hope now this video explained why classical mechanics got this graph. In the next video, we will discuss how it does not match with the experimental result and the birth of quantum mechanics. Thank you for watching this video. Please like and subscribe to help the channel grow. See you in the next video.